Hi, and welcome to the session Software Defined Networking Meets HPC. In this session, we'll discuss how cloud networking and SDN enables customers to run HPC applications at scale on Google Cloud. High performance computing is a foundational infrastructure for researchers and scientists for their computational needs. And HPC's importance is actually much more evident during these times like the COVID-19 pandemic. For example, scientists in the life sciences industry are seeing sudden demand for the computing needs and are increasingly turning towards cloud technologies for their computational needs. We are also observing the same trend of demand, in other areas of HPC like financial modeling and weather forecasting. HPC infrastructure can be quite complex and require highly specialized and very expensive infrastructure. With the advent of cloud computing, more and more customers are demanding the flexibility and agility of the cloud model for their HPC applications. So the good news is that HPC workloads can leverage cloud, and cloud can deliver the comparable, or better performance metrics for most HPC workloads. This quote from Andrew Sutherland of MIT sums it up quite well. How cloud computing can help their HPC application to do a much better job with HPC. In this presentation today, we'll share how Google Cloud can help your HPC application run in cloud and provide the best experience and meet your price performance objectives. My name is Manoj. I'm a product manager in Google Cloud networking team, and I'll be co-presenting this session. So this talk is primarily focused on networking aspects of HPC, but we'll also be discussing about other components of the infrastructure and services that's required to run HPC in the cloud. We will talk about some specific application benchmarks that provide insights into the capabilities of Google Cloud. Google Cloud offers the best-in-class infrastructure to run HPC applications. Our offerings provide a broad set of compute products to run tightly coupled and parallel workloads, including machine learning applications and high-performance data analytics workloads. These products are actually backed by Google Networking. And Google's networking is the same networking that is built and designed to run all of Google's billion plus user services. The services like Gmail, services like Maps, services like Search, everything runs on the same infrastructure as Google Cloud. We'll be discussing this in a lot more details in our next couple of slides. Google Cloud Platform also provides a very broad set of storage applications that helps you deploy HPC applications at scale on Google Cloud. We'll be talking a lot more about that in this session as well. Last but not the least, we have a very broad ecosystem of partners that helps us fill the gaps that we may have in Google Cloud. Specifically, when you look at the stack for HPC, it's actually quite deep. So things like schedulers and workload managers, we have a strong partner ecosystem that helps you fill those gaps. Our success in HPC is very evident in the broad set of successful deployments that we have across different verticals like healthcare, life sciences, financial services, education and research, etc. They run complex HPC codes like computational fluid dynamics and weather modeling with great success on Google Cloud at very, very high scales. This list is actually growing tremendously. As I mentioned before, we have a very strong set of ecosystem partners. As I mentioned, HPC is not just infrastructure, it actually has the stack that is very, very deep. So we have a very broad set of partner ecosystems that help you fill the gaps that you might actually have on Google Cloud. For example, workload managers and schedulers and system integration. So that actually helps customers to very quickly come onto cloud and deploy their applications as fast as they can. Now let's go and have a very deep journey into the networking stack of Google Cloud.
In the next few slides, we will show you how Google Cloud uses the power of software-defined networking to deliver high performance and low latency on a general-purpose multi-tenant cloud infrastructure. GCP supports up to 100 Gbps of bandwidth on a single VM and delivers latency as low as 10 microseconds between two VMs in the same placement policy group. So let's get started. Google was one of the pioneers of software-defined networking for both physical networks and virtual networks. Google's virtual networking SDN stack is called Andromeda. A key aspect of the SDN architecture is the separation of the control plane from its data plane. The data plane resides in physical switches, for example, the edge routers in a data center, and virtual switches like the hypervisor on every machine in the cloud. A logically centralized control plane has a complete view of the network as well as the customer intent. The controller then realizes customer intent across different data plane elements. For example, the Andromeda controller shown here in this picture takes a VPC firewall policy, translates it into appropriate rules for each host that's running a VM for that VPC, and then distributes that policy to the virtual switches on those machines. An important benefit of this architecture is that it scales better and removes the bottlenecks found in traditional networking. For example, it lets us provide the same VPC features to VMs, bare metal instances, and containers. The feature that is most relevant to high performance computing is performance. And in particular, the performance of the virtual switch that implements most of cloud networking's routing and security policies. So, how does Google build a fast virtual switch? The Andromeda virtual switch is built using a framework called Snap. Snap enables OS bypass packet processing pipelines in user mode. Snap supports running these pipelines on dedicated threads or in shared threads. Andromeda on Snap has two key components, a fast path and per VM coprocessors. The fast path packet pipeline runs on dedicated threads and it has a very small CPU budget, literally nanoseconds for every packet. More expensive pipelines such as NAT and DOS protection, they run in per VM coprocessors. So this architecture neatly enables us to achieve both high performance and isolation. That is, one VM's traffic does not affect another VM. Software tuning, such as dedicating threads and optimizing the number of instructions per packet, can only take you so far. To get true HPC class performance, hardware offloads have typically played a critical role. Andromeda started out its offload efforts with simpler offloads, such as TCP segmentation and send receive offloads. We then added encryption offload to it, as it was one of the expensive components of our packet processing pipeline. A recent enhancement, which is very relevant to HPC, is the introduction of zero copy payload transfers between a VM's memory and the NIC hardware. Andromeda still gets to process headers of packets, and hence it can continue to enforce VPC policies and rate limits, but there is no software involved in the movement of payload, which helps us achieve higher performance. So now let's see how well it works in practice or what performance we are able to achieve. This graph here shows how performance has been a big focus of Google Cloud Networking for many years, and we've been making continuous improvements in performance. Only the last two bars of this graph are relevant to current SKUs. We're able to hit line rate of 100 Gbps inside your VMs. And this is available right now on GPU attached VMs. Other types of VMs have up to 32 Gbps depending on the core count. So with that, we've solved the bandwidth problem. What about the harder problem of latency, which is also very critical to HPC workloads? For latency, the entire software stack, as well as the network connecting the VMs, play a critical role. We've looked at the virtual switch in the hypervisor at GCP. Now let's take a look at what's inside the guest VM and the rest of the HPC stack. In this figure, starting at the very top, are the applications. Tightly coupled MPI applications are written to MPI frameworks, and GCP supports both Intel MPI and Open MPI. These frameworks depend on either directly the Linux TCP/IP stack, or they access the networking stack through libraries like the libfabric library. Now, Google has invented many of the major improvements to TCP in the last few years, and we have one of the best congestion control teams in the world. Underneath the TCP stack are the drivers that interact with the virtualized NIC. GCP supports the generic WordIO driver, but recently we also introduced our own Google Virtual NIC driver. This GVNIC device exposes the best of Google's infrastructure to the guest OS. For example, the zero copy feature that I talked about is exposed by the GVNIC driver. Now, Google has one of the best performing SDN based physical networks underneath Google Cloud. But no matter how good the network is, one of the important things you can do to reduce latency is really place VMs next to each other. This is where the placement policy comes in. GCP supports two types of placement policies, compact and spread. VMs associated with the same compact placement policy are placed very close to each other in the data center. So now let's see how well all this works in practice. The graph here shows an experiment where we run the famous MPI ping pong benchmark on Google Cloud. The leftmost data point is the baseline latency between two VMs without any placement policy. And as you can see here, we get about 28 microseconds. By choosing the right VM type, in this case, the compute optimized VMs that Manoj will talk about in a bit, and associating them with a compact placement policy, we were able to get the latency down to 18 microseconds. So that's a good 10 microsecond improvement on the base latency in a zone. As we tune different layers of the stack that I showed in the last few slides, we see that latency continued to improve. And the bottom line is that we can get to under 10 microsecond latency on Google Cloud today, which is sufficient for running some of the most demanding workloads. Now, we don't expect our customers to make all these optimizations by hand. So we've created solutions guide as well as batch script that you can run inside your favorite VM instance types to activate these optimizations. So that gives you a flavor of how GCP leverages SDN to build the right network for HPC. This SDN-enabled network gives you low latency and high throughput. Your MPI traffic can leverage VPC features like the VPC firewall. And since all of this is built via software on general purpose infrastructure, high performance networking is available on many instance types, both general purpose as well as compute optimized VMs. Now let's take a look at compute and storage infrastructure.
Now that we understand a little bit more about the networking magic that connects everything together, let's talk a little bit more about what other components of the infrastructure is required to make a HPC application successful on Google Cloud. Google Cloud actually offers a broad set of compute products that can suit all kinds of applications, starting from web servers to network appliances, and of course, large scale, tightly coupled MPI and nickel workloads. The general purpose instances called the N2 series or N2 or N2D machines, they actually balance price and performance and are suitable for most workloads that you may have. But we have specialized compute optimized VMs called the C2 instances that offer high-end vCPU performance for HPC applications. We'll talk a little bit more about the C2 instance type in the next slide. We also have a memory optimized VM type called M2 that is actually suitable for your memory intensive applications like SAP HANA. For lower TCO application, TCO is actually very, very important for HPC because, as you mentioned before, HPC infrastructure can be quite expensive. So cost is very important for a lot of customers. So for customers like that, we offer the preemptible VM types. If your applications are designed as a fault tolerant application, and can withstand possible preemptions, then the preemptible instance type can save up to 80% of your time of your savings. We also provide the best accelerator actually in cloud, including the NVIDIA GPUs and Google innovations like tensor processing units to speed up your applications and give you faster timed results. Now let's talk a little bit about the compute optimized VM or the C2 instance types. Compute optimized VMs are well suited for HPC application, as I said before, both tightly coupled applications and high throughput applications. Compute optimized instances offer high end vCPU performance for compute workloads and offer up to 40% more performance compared to your general purpose VMs. They also leverage the second generation Intel Xeon processors and can run at a sustained clock speed of about 3.8 gigahertz. Additionally, this is actually a very important point. C2 VMs can provide full transparency into the architecture of the underlying server platforms. The NUMA topology is actually exposed into the guest operating system, and then applications can actually make smart choices to use the NUMA topology. This actually improves the performance a lot. You can choose a C2 instance up to 60 vCPUs and 250 gigabytes of memory and attach up to 3 terabytes of local storage. C2 instances can also deliver up to 32 gigabytes, 32 Gbps of bidirectional throughput today for the right CPU configuration type. And we have a very strong roadmap to basically improve this. And you can actually expect those high performance throughput instances to be on C2 instances. What we are observing is HPC and machine learning infrastructure are undergoing a convergence. We are actually seeing more and more machine learning workloads now using the HPC platform. GPUs are hence becoming a very integral part of HPC. GCP actually offers high performance GPUs on Google Cloud for machine learning, scientific computation, and 3D visualization. GPUs can actually be added to your VM instance type, and these VM instance types are highly configurable. We can attach storage, memory, bandwidth, and it actually acts like a regular VM for you. But you can attach up to 8 GPUs for these instance types. GPUs will also work with your GKA clusters, and GPU will also work with your preemptible VMs, which is actually a very common use case for HPC and ML. Now, one very important point that I would like to make is we have a very strong partnership with NVIDIA, and that actually helps us bring the GPUs the latest and the greatest GPUs that basically NVIDIA comes up with on our platform as fast as we can. Today, we support the Tesla platform, and in the future, in the very near future, we'll be supporting the NVIDIA's actually Ampere platform. From a bandwidth standpoint, we actually deliver up to 100 gigs on certain GPU types today. And this is actually in beta, but we have a very, very strong roadmap coming up. And you can expect that the higher throughput, which is very, very important for HPC, is going to be showing up for this GPU machine types in the very near future. Now, cost is actually very important for customers, as we mentioned before, right? So we have various programs and various options that's available for customers. For example, with preemptible VM types, as I mentioned before, you can actually save up to 80% of your cost. We also offer strong, deep discounts for committed and sustained usages. You could actually save up to 30 to 55% depending on how long you are using the VM instances. Now let's talk a little bit about the storage support on GCP. Storage is also very important, it's very complex, and as I mentioned before, the requirements for HPC applications are actually quite broad. Storage requirements for HPC, they're very similar to what any other regular enterprise application, but with some exceptions, right? Google Cloud Platform delivers various storage offerings like SQL, NoSQL, Blob, and Blog, and what have you. It's a broad set of offerings. But we have some offering that is very specifically designed for HPC. For example, we have object stores and file stores and a POSIX compliant parallel file system that is very widely used in the HPC space. But the very first step that a customer normally takes is how do I move my data from on-premise to Google Cloud? So for that, we actually offer a service called TSOP. Customers can use this service to hydrate their Google Cloud storage systems from on-premise. GCS or the Google Cloud Storage System is the Google Cloud's object store. And a lot of customers actually use this as primary storage, and there are other customers use this for actually archival storage on Google Cloud. We also have a broad set of NFS offering, both Google managed and partner managed. File store, Cloud File Store is our NFS file system, and the capacity that we offer today is about 60 TB. We have also announced the File Store High Scale offering, which can actually scale up to 325 terabytes. Customers also have the option to use EMC or NetApp if they choose that as their option. Now, HPC customers who are running tightly coupled applications or MPI applications, they normally require a POSIX compliant parallel file system. So GCP has partnered with a company called DDN, and jointly we basically provide an offering on Google Marketplace where they can actually use Lustre as their file system that has very high IOPS and scales horizontally for the HPC needs. So to sum it up, customers can then deploy the right storage system for the right application and get the best possible TCO. Now let us see how all these things come together in our next few slides.
So now that we gave you a glimpse of the building blocks needed to build an HPC solution, we'll take a look at two specific workloads. The first workload is a weather forecasting workload. It's a benchmark that many customers run on-premise on their state-of-the-art dedicated InfiniBand clusters. The first line on this graph shows the performance some customers get on-premise. Faster completion, which is lower value, is better in this case. The second line shows how this workload performed on GCP without many of the optimizations we talked about today. Once we applied these optimizations that we discussed, plus some workload-specific tuning, we were able to not only match the performance the customers get on-premise, but we did it with 30% fewer CPU cores. Now, there are additional optimizations that we've not shown on this graph that can bring down the completion time even further. But you're not always shooting for lowest latency, but the best price performance ratio for your workload. And this workload, this benchmark, demonstrates that really well. Let's also look at the LS-DYNA workload. This is a well-known workload in the automotive industry that does crash simulations. This workload is notoriously tricky to scale. The two graphs here show two different configurations of this workload. As you can see that with the help of the optimizations that we discussed today, this workload scales quite well up to multiple hundreds of cores on GCP. This is as good as what our customers are able to get on-premise on a dedicated specialized infrastructure. We've looked at many such workloads. We only discussed these two. And what we find is that for each workload and a given data set, there is a sweet spot in terms of price performance ratio. Once you have the right set of tools, you can easily find that sweet spot and provision and pay for just enough infrastructure for your workload. And cloud lets you make that trade-off, which was not even possible on-premise. So in summary, we would like to leave you with three key messages. One is that you no longer need to pay for a dedicated specialized infrastructure to run HPC workloads. Google Cloud makes available to you the best-in-class infrastructure that we use to run our own high-performance and AI machine learning workloads. Anyone can get access to this infrastructure on demand and pay only for what they use. Number two, HPC is a huge area of investment for us. We built a number of solutions for various industry verticals, and new ones are being added to it every day. Number three, if you don't see your workload listed here, please do let us know. We want to make sure that Google Cloud is the best at running all kinds of high-performance computing as well as high-performance data analytics workload. Thank you.
Thank you.